MATLAB provides a complete integrated workflow for engineers and scientists to explore, prototype, and deploy deep learning algorithms in a familiar development environment with built-in higher-level apps and libraries. You don't have to be limited by the lack of data scientists or deep learning experts in your team, or have to cobble together various tools for a complete workflow. MATLAB also supports interoperability with open source deep learning frameworks using ONNX import and export capabilities, so you can use MATLAB tools alongside Python and or C++ to best suit your needs, such as for design exploration, visualization, or deployment, to name a few. You will find many other deep learning application examples from the links under this resources section below to get started with applying deep learning to your application area of interest. In this video, we will consider an industrial application where we will use deep learning to classify defective parts on an assembly line and focus on deploying such an application to an Arm Cortex A based platform. Here is the complete inference pipeline for this application with image acquisition, pre-processing and post-processing around a trained network. The trained network is an outcome of the training process, and if you're not familiar with that workflow, please refer to the resources section. Using MATLAB Coder, you can generate code for the entire application and deploy to any Arm Cortex A based platform like the Raspberry Pi or HiKey 960 or NXP i.Mx family of processors, to name a few. Here we have the MATLAB code for the entire algorithm, and I'm going to quickly highlight the pre-processing and post-processing code here. Pre-processing code that extracts regions of interest and resizes the images that are passed to the trained network, and the post-processing code that annotates and labels the parts based on the predicted output from the network. Now, in MATLAB, I can test my application on test images, or I can also connect a sensor, such as a webcam, to my desktop and use the live data to test the robustness of my algorithm. You can then generate C++ code for all parts of the application using CodeGen API or the MATLAB Coder app. Here we are generating code from the trained network portion separately, and this generated code for the deep learning network leverages the Arm compute library for acceleration. Next, we generate code from the pre-processing logic as shown here, followed by code generation for the post-processing logic, and here in the generated code folder, you can see the generated code for the different parts of the application. Finally, I can deploy the generated code by downloading and building the code on my target device, which is a HiKey 960 board. This board from Huawei has 4 ARM cores, 4 A73s and 4 A53s in a big. LITTLE architecture. The Arm compute library enables you to deploy the trained network efficiently on Cortex A CPUs and, if present, Mali GPUs. Please refer to the resources section on the detailed steps for compiling and deploying the code using the generated makefile, like setting the appropriate environment variables and using the compatible versions of Arm compute library, OpenCV, etc. on the target board. This example application has relatively low frame rate requirements, and so such applications can be deployed on Cortex A platforms or even Cortex M platforms. Furthermore, the application is also using multiple CPU cores on the HiKey board through Arm Compute, since the Arm Compute library was built with OpenMP. And the generated code using Arm Compute leverages the available cores accordingly on your target hardware, as you can see here. You can try this example for yourself by going to the file exchange link listed under the resources section.